Very good morning to fellow panelists and friends. My name is Min Kang, BSc Physics final year student for University Malaya. Today I'm gonna talk about my internship projects that I've done for the past 2 months in National Astronomical Research Institute of Thailand, NARIT. This internship project is supervised by Ramkesh, the research scientist in NARIT, specialized in star formation. So the story went like this. The first day I arrived at the internship, Mr. Ram just told me, hey, I think this region W40 is interesting. Why don't you go and study everything about it? And then here's my result. There are 3 objectives that I want to achieve in this study. First, I want to look at structures of a bipolar star-forming region using continuum and spectral analysis. Second, I want to understand how massive stars influence the surrounding medium. Finally, I want to know how do massive stars form? What's the condition forming massive stars? Different than our sunlight stars. And with that, I would like to thank both NARIT and University Malaya for providing me hospitality for the executions of this project. So let's start with apparatus, since I'm doing experimental stuff, right? By the way, astronomy is very hard to do experiment on hand. So what I call it is observational science. Means I observe the region using multiple techniques and trying to get information from that. So these are the telescopes which my data came from. Basically different, separated into continuum and spectroscopy, including ground-based telescope and also space-based telescope and airplane-based telescope. So I'll be using data from these telescopes for my analysis of W40. So let's start with stellar evolutions. How do stars form and die? Everything starts from the place which you have materials for forming stars, gas and dust. And we call that star-forming nebula. And depending on the mass of stars formed, they can have different paths. This is a sunlight star, and this will be the path for massive stars. Wouldn't focus on that. Instead, we'll focus on star-forming nebula, because that's the place I'm looking at. And also, this place contains massive star. 2 examples of nebula, the Orion and the W40. My subject interest is another type of nebula known as W40. So this is the bipolar star-forming region, actively forming stars, slightly above the Milky Way galaxy plane, 7.5 light years across. And the reason why it's interesting is first, there's a cluster of very massive stars in the center. Second, you can see the bipolar shape revealed by infrared image, and I want to know how it is formed. How do I study this? Again, I use observational science. Means I look at the light emissions from that region. There are 4 processes basically giving me the emissions. First, when the molecule undergoes rotational transitions, it emits electromagnetic spectrum. And the frequency depends on the energy level of that transition. Second, there are dust grains that emit black body radiations. And as you would expect, for black body radiations, the wavelength depends on the temperatures of the dust. Third, it's a special kind of molecule, organic molecule known as Power molecule, and it gets excited by UV radiations and gives us emissions in infrared at certain wavelengths. So you can see, these astronomical objects has not only the continuum by the black body radiations, but also some specific wavelength with the emissions from the Power molecules. 3.3, 6.2, 7.7, and so on micron. Finally, when you have a region with abundance of ions and electrons, recombination process might occur. Ions capture electrons and giving out recombination line. 2 examples are H-Balmer series and H-Lyman series. With this, I will expect to see quite distinct structures across different wavelengths, even at the same object, because different mechanism giving out emissions, right? So this is exactly what I found in W40 at 1.23 micron, at 8 micron, finally at 500 micron. So the longer wavelength is particularly interesting because these emissions is where the star formations might be happening, or might be the future place for star formation. So let's focus more about the longer wavelength analysis. Let's look at the star formations process. So this is the overall idea, right? Basically, collapsing cloud forming clumps, cores, accretion happens, heating up the gas, young stars form, eventually nuclear fusion kicks in, and stars are formed. Planets form, gas and dust clear up. So as you can see, along this process, the temperature is getting higher and higher. That's why we need multi-wavelength analysis to probe different stages of the evolution, right? Using black body radiations, of course. Okay, so depending on the mass of star form, as I said just now, it could start to influence the mother cloud, the clouds which it is formed. So let's see what happened to interstellar medium surrounding a massive star. This is a diagram. Basically, you start with a high mass star giving out strong UV radiation. And the most abundant species in the medium is hydrogen in the universe. So hydrogen will start to get ionized by the UV radiations to form an H+ ionized region. Slightly away from that, you start to have a region which weaker UV radiation wouldn't be able to ionize hydrogen, but still able to ionize other atoms. Dissociation region. This is where you see atoms like hydrogen and oxygen. Also the place which you would expect C+. Also the place which you expect to see PAR molecules, because they get excited in this region. Moving away from this region, you start to have a calm, uninterrupted region. We call that, dusty molecular cloud. So the end, the right hand side. This is where UV radiation is shielded and destroying of molecules wouldn't happen. Also the place you can start to have complex molecules like H2O, like carbon monoxide. Also the place which you can have star formation because the UV radiation couldn't destroy the molecules there. To support this theory, I'm looking at W40 to find observational evidence. And I found two. So the first one is, I propose that we're looking at H on, so everything just stacked together. The second is more direct, which I can actually see there's a massive star here, followed by ionized gas, second layer, PDR region, photodissociation region, finally the cold molecular region, supporting the idea stated by this 1999 paper. Okay, so to further analyze this region, there's a need to combine different wavelength observations into one, because as I say, they give different features. So this is a composite image I've done with 3 wavelengths, and I labeled them using red, green, and blue colors. So you can see the wavelength over here. And I look at this, I want to find if this region supports the formations of H2 region. This is the theory that says you have a molecular cloud in the middle as a filament, massive star form, ionize the surrounding medium, and when the gas reach the H after the expansion, the gas escape and form a cone shape. Indeed, I found a cone shape in the blue color emission here. This blue color is denoted with H2 region. And also, the red color label shows the emissions of dust, which supports the filament tree structure. But one thing is curious, which is the green, the PAR molecules, the PDR region, seems to be not so symmetrical with the rest. It's like going to the left a bit. And this is the cautions when you're looking at 2D image. right? When you look at 2D image, you wouldn't know the 3D structures. So perhaps this could be a foreground, this could be background, nobody knows. This is where spectroscopy comes into handy. And to introduce spectroscopy, I would like to introduce the Doppler effect. So the same as how you listen to different pitch of ambient sirens moving, you also would expect to observe the emissions of astronomical source to shift to a different frequency depending on the motion. So instead of putting frequency as the x-axis, I put the velocity to show you how the molecules giving off the emission is moving. Right? And the spectral analysis basically giving me four things. Peak line strength and intensity tells me how abundant the molecules are in that region. The velocity at the peak tells me the motions of the molecular cloud, and the line width tells me the velocity dispersion of how chaotic the cloud is I'm observing. Having known this information, I plot all the molecule distributions on the same plot, and there's a specific region interested to me, which is here. So this region has all the molecules observed, and as you can see, the molecule HCO plus is the most abundant, followed by the HCN and the carbon monoxide. So looking at the evolutions of chemistry, it tells me that this cloud is highly evolved. It's not a new cloud, and it's been influenced by the UV radiation here. So that's why you see lots of HCO plus. Back to the question of whether something is foreground or background, I probe the emissions of PDR region, right, using carbonized carbon, C2 emission here. So the z-axis here is the velocity, as I tell you, the x-axis, velocity structures of the cloud. I notice a gap in between. I propose that instead of looking at the cloud, I'm looking at actually two expanding clouds, one away from us, the other one towards us. And to further support this idea, I plot all the molecular clouds velocity distributions on the same 3D volume rendering diagram. And as you can see, the gap in between is filled by carbon monoxide, and the HCN HCO plus trace quite well with the PDR region. I propose that 7 km per second is the rest frame of the W40, and the other two, they are expanding at 2 km per second away from the center. So that's an expanding cloud. Finally, to look at the probe into the science of star formation in W40, I compared the observational results, the image, with the model. So this is a famous model called radiative implosion model. It basically means you have a massive star with strong UV radiation, and the radiation could influence a distant cloud, right? Not in surrounding, but a distant cloud. By first, ionize the front part, dissociate the second layer, compress the molecular cloud behind, and the compression will trigger a star formation. So the observational evidence will be like this, a V-shaped structures pointing towards the massive star. Try to find in W40 to see if there's any star formation. As you can see, quite interestingly, the H and the G region is very far away from the center massive star, the plus signs here. And it's kind of impressive to see how a massive star could influence the cloud at such a distance. So my conclusion here is W40 is a birthplace of massive stars and will be a future birthplace of stars. And the stars here influence the medium, causing expansion in H, the PDR region, compressing the molecular clouds to form another star formation. While massive stars live and die young, obviously they are not habitable because UV radiation too strong. But for me, they are the crucial thing for future star formation. And this is exactly why we need massive stars to form stars like our sun, so that we can have solar system that could support life just like our Earth. That's all of my presentations. I shall leave my summary and future work here. Thank you so much for listening. Thank you.
Thank you, Lim Min Kang, contestant 1, for your hard work and great presentation about the presentations. We will now open the floor to the judge for a Q&A session for 15 minutes. Judge, you may begin asking questions now.
Me.
I'm not space physicist, but I actually verified my concern with a space physicist that she actually is using. You have a very thorough findings and presented well, but it's just that the issue is, I find it difficult to find what's the motivation of this study.
The motivation of this study. Can I change my slide to another? So the motivation comes from actually this region, right? It's not a typical star-forming region. So just now I was showing all the models to find signs of star formations and the formations of region, right? But in this case, it is quite complicated, in which you cannot just look at the image and say, this is how the region is formed. Means that the current models to explain the typical star-forming region, the formation model, the chemistry model, not really holds true for this particular region. Because, again, we might be looking at two different structures overlapping each other over here. So, current model is definitely not enough to analyze such a complex structures. That's the first motivation why I want to probe into details now. And the second reason is because astrochemistry is a relatively new field, right? With the current technology of telescope, we can start to observe the emission lines from lots of molecules, carbon monoxide, different isotopes of carbon monoxide, HCO+, all those molecules is a new way to probe the evolutions of a region, right? Because if a region have, let's say, lots of HCO+, based on this model, it means that the cloud is evolved, not young, but old. But if it has a lot of N2H+, means the cloud might be young. So we wouldn't know which cloud is young, which cloud is old, which form first and which come next. And with astrochemistry, we are starting to be able to do that, to see the overall time scale of the region. Instead of just looking at this and say, okay, this is a H2 region, we're looking at how this is formed and why it is formed that way. So that's my motivation. I hope that answers the questions.
No, okay, next question. Okay, I think a general question from me. I don't know if you have a background in astronomy or astrophysics before, but how can you relate what you have learned before in your undergraduate course with this research? How it can help you or how it relates? Okay?
Okay.
You got it, question?
Yes, thanks. First, I took a basic introductory subjects in astrophysics, and the theory of the emissions helps me a lot, especially, let's look at this. So this, first I learned black body radiation, greatly applicable to my study, because most of the stuff are black body radiations, and also the spectral line. Okay, the spectral line is more to quantum mechanics because you have different rotational transition, the J and the L. But studying those in undergrad helps me in this study too, right? I would say more fundamental things that could combine together to get me and analyze the emission. Otherwise, I wouldn't know what the line tells me. It might be just a random line from nowhere that I wouldn't know. But those are two. And the final thing is, again, all the theoretical thing, like the formations of stars that I learned in astrophysics, and also evolutions of stars, might not apply 100% to this region, as I say, complex, but still, in a way, it helps to kickstart the journey of understanding a complex cloud, for example. Yeah.
Okay, so show the conclusion part. I'm not sure whether I can ask my questions in a way that I can express it myself. So you are working, trying to make the conclusion based on your evidence.
Yes, my evidence.
Everything that you present appears to be positive. You measure, you get this, you get that, everything seems to fall into. Then you have a proposition, you have a model, you have data, then you say, okay, my data verifies my model, therefore you have all these conclusions.
Yes. Not all.
So I think my question is, at what point do you think that your conclusion may be wrong? I'm not saying that your conclusion is wrong, but because you have something that in your mind and you are trying to verify things,
Yes.
would you consider that how to falsify your findings? What are the things that you can tell me that may point to the possibility that your conclusion is wrong?
Definitely, I have lots of self-doubt during this project. I put it in my future work. So first of all, the VRC structures, the V-shaped structures, might not actually be the good place for star formation without knowing the mass of the cloud or the chemical compositions in detail. Second, I don't know what's the source of expanding PDR. I'm proposing it's caused by massive star, or it could be different mechanisms like stellar wind. Third, everything I've said here could be a projection effect. If I'm looking at this row as a whole, there are 5 people, right? And the emission might come from you, or the person at the back just happens to have long wavelength that pass through all the others and reach me. So this is a projection effect. I have to look into the other angle to actually see 5 people. So this is one thing. I couldn't tell if the region, the structure is angled towards me or not, or it's a face on, or it's a edge on. And all of this could heavily influence the result. It might be a projection effect. I might not actually looking at emissions from you, like from other. So, yes.
So when you verify something, right? So you have some idea you want to prove that you. So you also mentioned that there are some uncertainty in your methodology, and there might be. So there are some uncertainty that you have not ruled out. So have you ever attempted stress tests on your findings? Stress tests here means you were thinking that maybe what you are doing to verify what you think may be not right, but if it's right, then you should pass another feedback. So by using different stress tests, you would be able to strengthen your conclusions. But have you tried that? To convince yourself is that that your finding is actually correct, not only using this method, but also other independent methods. You get my question?
Yes. Thanks. First of all, data given to me from my telescope observations, I have no way to ask the telescope to do an observation again. So that's one. The data given me is final. I couldn't do anything about that. Second, indeed you are right. All these emissions I could fit a Gaussian to see how it differs from the Gaussian. And doing that, not showing here because it's not complete. Everything that I show here is initial visual inspections on the possibility to go further. Of course, lots of tests could be done. One is feeding Gaussians and feeding quantum mechanical hyperfine structures on some other lines to see how they agree with the Gaussian. The second is to calculate the mass and the mass of cloud to see how they agree with the previous literature. If you have a mass of very low mass but you claim it's a star formation, things might get a little bit wrong. Still doing, not showing today, but everything here is I would say, possibility or proposal, not like 100% verified, because things could change. Also, the resolutions of observations could mean a lot. For example, this radial velocity, the telescope resolution is about 0.4 km per second, right? So if you have a telescope which is capable of future telescope, 0.004, a magnitude higher than that, it might not be a Gaussian in the end, it might be too Gaussian, just because of low resolution. So that's one of the fallback of getting lines from current telescope.
Spectra is for all the molecules.
All the observed molecules that I have.
Why are they all of the same frequency?
Yes, good question, thank you. As you would see, right, the x-axis is the velocity. So using the formula that I showed here, instead of putting frequency as the x-axis, I've already do these calculations to convert everything into velocity and set 0 km per second as the raised frequency of the emission. So everything has been shifted such that the 0 km per second shows the rest frequency of the particular transition emission. And that's why you see everything kind of falls at 5 km per second. Shows that all the molecules have similar motion and they could be in the same cloud. That's why the cloud is moving at 5 km per second, line of sight away from us. So that's how you see all in the same graph.
You mentioned about compression. Compression, what the mechanical behind compression?
No. So let's go back to here. As I mentioned, this dusty cloud could be the star formation place. Right? So what causes the compression is when the radiation is ionizing the the hydrogen molecule or atom, starting to form H+ region. So H+ is more energetic, higher kinetic motion, hotter. So the average distance, the density could be reduced because their motion is more aggressive. And if you decrease the density here, the gas is actually going to push away and indirectly pushing the dusty cloud so that its density increases to a point where it exceeded the gene mass, that's the mass limit to form a star, and stars to be formed. And the same goes to the DRC model here. Basically, all the compression is caused by the expansions of the hotter gas ionized by the star. So, pushing away from that.
So with the compression includes the expansion of the hydrogen ion.
Yes.
That how are the gravitation?
Gravitational effect is mentioned in gene mass. So if the mass of this the clouds increase, it exceeded the gene mass, so the internal motions of clouds will be less than the gravitational attractions of the molecules. So molecules start to collapse and density gets higher, stars form. That's the mechanism. Gene mass is a threshold.
You mentioned just now the velocity distribution.
Yes, not exactly. I mentioned the chaotic motion can be traced by the line strength, the line width over here, the width of the Gaussian, not the central velocity. The central velocity traces the cloud moving as a whole, but within that cloud there might be internal motions that causing small shifts that causing the broadening of Gaussian.
And complex finally more complex molecule, can you give some example of complex molecule that you mentioned? I heard you mentioned H2O and CO are complex molecules. Are they really complex molecules?
Final question? Okay. Yes, it is complex molecule in a astronomical sense because where is the okay here. So beyond these clouds, right, UV radiation is interfering with the formation. So you can't actually see even carbon monoxide from forming because the CO will get dissociated by the UV to become C and O. Of course, there are a lot more complex molecules such as the PAR molecule, the organic compounds, the water, everything molecule. The reason why it's formed is because it's uninterrupted by the UV radiation. That could dissociate them. So in a sense, it is called complex, and there are other more complex molecules, of course, like the long chain of organic molecules to form.
Atomic molecule should not be called complex molecule.
I'm sorry to interrupt the judge. The time given 10 minutes up. The 15 minutes is up. We will now be moving on to the next contestants.